The question is about magnetic moment. If Hund's rule is not followed, magnetic moment of Fe2 plus, Mn plus and Cr, all having 24 electrons, will be in the order. We all know that magnetic moment is directly proportional to the number of unpaired electrons. Let's find out the unpaired electrons in these ions and atom given. Let's take Fe2 plus, Mn plus and Cr. The valence electrons of iron is 8 minus charge. So we will get D6 configuration. Manganese valence electrons are 7 minus charge ends with D6 configuration. Chromium valence electrons are 6, no charge on that, ends with D6 configuration. We all know d orbital is degenerate and it has 6 electrons in all these ions. Let's write the electrons this way and the 6th electron get paired up. Here we understood if Hund's rule is not followed, then usually electrons occupy the lower orbitals. Therefore, this electron comes here, get paid. Here, this comes here and get off paid. And finally, the orbital picture ends this way. 1, 2, 3, 4, 5 and 6 electron, and these two remains vacant here. As no unpaired electrons are seen here, the magnetic moment remains 0 for all these 3 ions and atom. Therefore, magnetic moment will remain equal in all these ions and atom. So, our answer will be A option. In this question, we are asked the stability of the two oxidation states correctly represented. Stability can be understood with respect to electronic configuration and hydration enthalpy. Here, for these following ions, let's find out the D configuration with the help of electronic configuration. Titanium 3 plus and titanium 4 plus. The valence electrons of titanium is 4 minus charge, it is D1 configuration, whereas here 4 minus 4, it has D0 configuration. This should be more stable, but it is given wrongly here. That is not the option. Second option, Mn2 plus and Mn3 plus. Manganese valence electrons are 7 in number. Minus charge 2. It ends with D5 configuration. Completely half-filled stable configuration. Half-filled stable configuration, whereas here 7 minus 3 ends with D4 configuration. Mn2 plus is more stable compared to that of 3 plus. Therefore, this option should be correct, and that is the answer here. But let us find out the rest two also. Fe2 plus and Fe3 plus. The valence electrons of iron is 8 minus charge 2, it ends with D6 configuration, and here 8 minus 3, it is D5 configuration. This should be more stable, but it is given the other way here, so that is not the option. Whereas D option, Cu plus and Cu2 plus, the valence electrons of copper is 11 and charge minus 1, it has D10 configuration. And here 11 minus 2, it is D9 configuration. Despite D10 configuration, Cu plus is unstable, Cu2 plus is stable due to its high negative hydration enthalpy in aqueous medium. As Cu2 plus has high negative hydration enthalpy, it will be more stable compared to that of Cu plus. It is other way given here, therefore that is the wrong option. For our question, B will be the answer. Which of the following catalyst is not correctly matched with the reaction? The reactions are this way. Vanadium oxide in contact process for oxidation of SO2 to SO3. SO2 will get oxidized to SO3 in presence of vanadium pentoxide in contact process. So this statement is correct. Second statement, finely divided iron in Haber's process is used as catalyst. N2 reacts with H2 of 3 moles to give 2 moles of ammonia in Haber's process, where we use finely divided iron powder as a catalyst. This statement is also correct. Third statement says iron 2 catalyzes the reaction between iodide and persulfate ion. Iodide and persulfate ion, that is S2O8 minus, in the presence of Fe3 plus, that is Fe3, they get formed with I2 and sulfate ion here. Actually, when we look into the mechanism, first ferric ion reacts with the catalyst, reacts with iodide, and it forms Fe2 plus, meaning ferric will get reduced to ferrous ion and oxidizes I minus to I2. Later, next step, ferrous ion reacts with persulfate ion, that is S2O8 minus, and it will form Fe3 plus, where ferrous get oxidized to ferric and persulfate will get reduced to sulfate ion. Here the products I2 and sulfate are formed and ferric ion is regenerated, which is the catalyst here. Therefore, in this option, Fe2 is the wrong statement. It should be Fe3. Therefore, the answer for this question should be C option. Let's check with the next one also. We understood that nickel in presence of hydrogen for conversion of vegetables oil into ghee. Vegetable oils in the presence of nickel catalyst or palladium or platinum, it gets converted to oil, meaning ghee. So our answer should be C option. Which of the following is not correctly matched? Not correctly matched. Let's take one by one. An element of first transition series with highest third ionization enthalpy, zinc. To find out the ionization enthalpy's strength, we should know the electronic configuration first. Zinc has electronic configuration in its ground state as 3d10 4s2. Third ionization enthalpy, meaning after losing these two electrons, the third electron has to be lost from this d10 configuration. As d10 configuration is highly stable, it is not that easy to remove the electron from this configuration. So third ionization enthalpy will be very high for this zinc. the first statement is right. Second statement, an element of first transition series with the lowest enthalpy of atomization. Enthalpy of atomization, otherwise boiling point. Boiling point decreases with a decrease in number of unpaired electrons. Zinc has 3d10 4s2 configuration followed by argon configuration, and here zinc shows D10 configuration where the electrons are completely filled. Therefore, no unpaired electrons. No unpaired electrons will lead to very poor interatomic metallic bonding between zinc atoms. Zinc atoms will have very poor interatomic metallic bonding or no interatomic metallic bonding. Therefore, they have low enthalpy of atomization. The second statement is also right. Now, third statement, an element of first transition series which has highest second ionization enthalpy, copper. Its ground state configuration is 3d10 4s1. They are talking about second ionization enthalpy, meaning after losing S1 electron, the second electron should be from D10, that is second ionization enthalpy, and this second ionization enthalpy obviously will be very high as it is a stable, completely filled configuration. So this statement is also right. Now fourth statement, last element of third transition series is cadmium. Three D block elements are in first transition series, second transition series and third transition series respectively. The last element of first transition series is zinc, then cadmium and then mercury. The question given here is the third transition element is cadmium, which has to be mercury, not cadmium. Therefore, this statement is not correct statement. So finally, our question answer will be D option. The question is the equivalent weight of potassium permanganate when it is used as an oxidant in neutral medium. Potassium permanganate in neutral medium will get reduced to manganese dioxide, where manganese will be in +7 state in permanganate and +4 state in MnO2, meaning permanganate, the manganese ion which is in +7 will gain 3 electrons and get reduced to +4 state. It get reduced to +4 state, meaning the number of electrons gained by potassium permanganate gained by KMnO4 is nothing but 3 electrons, which is nothing but n factor. It is the n factor. Number of electrons gained is the n factor. Now, equivalent weight of any substance, or as we are talking about an oxidant, equivalent weight of an oxidant will be its molar mass by n factor. So, n factor is found as 3, so it should be m by 3. So, our answer should be C option for this. The question is like this. If KMnO4 is reduced by oxalic acid in acid medium, then oxidation number of manganese changes from what to what is the question. Potassium permanganate KMnO4, which has permanganate ion in the presence of acid medium, where get reduced by oxalate ions into Mn2 plus ions. Permanganate ion will get reduced to Mn2 plus by oxalate ions in acid medium, where when we calculate the oxidation number of manganese in MnO4 minus, it is plus 7, whereas here it is plus 2, meaning oxidation state of manganese reduces from plus 7 to plus 2. So our answer should be C option here. The question is like that: the number of moles of permanganate needed to react completely with 1 mole of ferrous oxalate in acidic medium. How do we solve this question? First, we will write the reducing reaction and oxidizing reaction. Permanganate ion MnO4 minus in acid medium, it will get reduced to Mn2 plus in the presence of ferrous oxalate. When we balance the reaction, there are 4 oxygen here, so we will add 4 H2O molecules here, and 4 2s are 8 hydrogen. We will add 8 H plus here. To balance the charges, we have to add 5 electrons this side. And now our ferrous oxalate is a special substance where both ferrous ion will get oxidized to ferric ion and oxalate ion will also get oxidized to carbon dioxide. When we balance here, ferrous ion will lose 1 electron and get oxidized to Fe3 plus. Oxalate ion, 2 carbon atoms, I'll put 2 here, and there are 4 oxygen here, 2 2s are 4 oxygen. To balance the charges, we will add 2 electrons this side, meaning 1 molecule of ferrous oxalate will lose 3 electrons and get oxidized in the presence of permanganate. Let us copy that reaction here, where FeC2O4 will get oxidized to Fe3 plus and carbon dioxide by losing 3 electrons. For equating the number of electrons, we will multiply the whole reduction reaction by 3, whereas this reaction by 5. So finally, we will end up with 3 molecules of MnO4 minus and 5 ferrous oxalate FeC2O4. These are the stoichiometric coefficient where 3 moles of permanganate ion will react with 5 moles of ferrous oxalate compound. Now our question says that how many number of moles of permanganate is required for reacting with 1 mole of ferrous oxalate, meaning to react with 1 mole of ferrous oxalate, how many moles of permanganate is required? Therefore, our answer will be 3 into 1 by 5, that is 3 by 5. So, our answer should be A option, 3 by 5. The question is like this: number of moles of potassium dichromate reduced by 1 mole of stannous ion. For this, we have to write the reduction and oxidation half reaction. Potassium dichromate, the dichromate ion. Dichromate ion in acid medium will get reduced to chromium ion. When we balance the reaction, as there are 7 oxygen here, we will put 7 H2O here. 7 2s are 14 hydrogen, so we will add 14 H plus. When we balance the charges, finally we end up with 6 electrons and 2 chromium ions here. Whereas stannous, in the presence of dichromate ion, will get oxidized to stannic ion. When we balance the charges, we have to add 2 electrons this side, stannic ion side. Now, to balance the number of electrons in the reduction and oxidation reaction, we will multiply the whole reaction by 3. So, finally, we end up with 1 dichromate ion will oxidize 3 moles of stannous ions. Our question is, how many moles of dichromate ions are required for reducing 1 mole of stannous ion? So our answer should be 1 into 1 by 3, that is equal to 1 by 3. So our answer should be A option here. The question is like this. In dichromate ion, every chromium atom is linked to how many oxygen atoms? Dichromate ion structure will be this way. Dichromate ion will have 2 tetrahedras which are linked by each other by a bridge bond like this. This is one tetrahedron of one chromium ion where it binds to oxygen atoms this way, and here also one tetrahedra where the axis will link with oxygen atom this way. Here both the chromium atoms will link with each other by this oxygen at the apex, meaning CR-OCR bond, they get linked. Here every chromium atom is linked to, look at this. This is one chromium, 1, 2, 3, 4. Meaning this chromium is linked with this 4 oxygen atoms, whereas this chromium 1, 2, 3 and 4 oxygen atom. This is also linked with 4 oxygen atom this way. So our answer should be 4 oxygen atoms. Every chromium will link with 4 oxygen atoms. So option D will be our answer. The question is like this. Match the column 1 properties with column 2 metals. Here the questions are like this. Element with highest second ionization enthalpy, third ionization enthalpy. To understand ionization enthalpy, it is very important to know the electronic configuration of the atoms. Let's write the electronic configuration of atoms. Chromium, copper, zinc and vanadium. They have ground state configuration like 3d5 4s1, copper 3d10 4s1, zinc 3d10 4s2, vanadium 3d3 4s2 in their ground state. By losing one electron, meaning first ionization enthalpy, the configuration becomes 3d5, 3d10, 3d10 4s1, 3d3 4s1 respectively. When they lose second electron, the ionization enthalpy 2 of these ions will become 3d4, 3d9, 3d10, 3d3 respectively. Here the question is element with highest second ionization enthalpy, meaning after losing first electron, this is the condition of the ion. To remove that second electron, that is second ionization enthalpy, high for what? We can see here 3d10 configuration. which gains extra stability due to D10 configuration. Therefore, copper should have very high IE2 value. Whereas third ionization, highest third ionization enthalpy here, meaning after losing 2 electrons, the configuration is like that, and to lose the third electron, that is IE3, what happens? When you look at these configuration, 3D10 is stable configuration, difficult to remove the electrons from that extra stable orbitals. Therefore, zinc should have very high third ionization enthalpy. Now, when you look at this, element with the highest second ionization enthalpy is copper, that is A, whereas third ionization enthalpy is zinc, that is B here. So options, when you look at the option A 2, B 3, A option should be correct. Let us check with the remaining options also. Here M in MCO3 6 is any one of this, chromium or vanadium should be the answer. Here chromium has valence electrons 6 in number. If at all chromium uses its 6 electron, and carbonyl, 6 carbonyl will give 12 electrons, and 6 plus 12, it will give you 18 electrons, stable noble gas configuration. So many chances of chromium to make complex with carbonyl like the CO6 should be CrCO6. If we check for copper, copper valence electrons are 11, and when it combines with 12 electrons given by carbonyl ligand, 6 carbonyl ligands, then it will be 3 and 2, 23 electrons, which is not possible. Whereas with zinc, zinc has valence electrons 12, and when it takes 12 electrons from carbonyl ligand 6 in number, it becomes 24 electrons, which is also not possible. When we check with vanadium, vanadium has 5 valence electrons, and it combines with the 12 electrons of carbonyl, it becomes 17 electrons. Therefore, it is also not possible. Chromium can make bonding with 6 carbonyl ligands. Therefore, for C option, 1 should be the answer. 1 should be C. Element with highest heat of atomization, the leftover is vanadium here. Vanadium, when we want to understand the heat of atomization, vanadium electronic configuration has to be known. That is 3D3 4s2 configuration here. Here 3 electrons are free to involve in interatomic metallic bonding between the vanadium atoms. This way, the strong interatomic metallic bondings will increase their heat of atomization. When we look at chromium, chromium has 3d5 4s1 electron. The unpaired electrons here are 6, whereas in vanadium it is 3 unpaired electron. Still, vanadium is having more heat of atomization compared to that of chromium, comparingly less heat of atomization here. Why? Because these 3d5 4s1 electrons are strongly held by the nucleus, as they are symmetrical, completely half-filled degenerate orbitals. They are held tightly by the nucleus. They are not easily available for interatomic metallic bonding. Therefore, comparing with chromium, vanadium will have high heat of atomization. So for D, 4 should be the answer. So when you look at the options here, A option is suitable for all this. A 2, B 3, C 1 and D 4. 4 should be the answer.